In a Friedman test, different formulas are used to calculate the test statistic when there are no tight scores and when there are tight scores. So in this particular example, I'm going to show you how to calculate the Friedman statistic when there are indeed scores that are tied. Okay, the data here is from table 5.3 on page 102 in the textbook. It have the same scenario, so 7 employees in the company were given different policies on how their tardiness was handled by the manager. 7 of them, there's nothing happens if they're being late to work in the baseline month. Month 1, every time an employee is late to work, $10 taken off the paycheck, and the second month, every time an employee is being late to work, $20 taken off from the paycheck. In this particular scenario, we have tight scores. For example, here you have 2 10s and you have 2 2s. The reason we're looking at the tight scores within observation, if you can remember from the last video, is because the scores are ranked within the same observation. Alright, let's start, and first we look at the formula that's necessary to use when there are tight scores. Here it is. It's available in the textbook as well. And we go through the formula, we find out, okay, N, K, Ri squared, and Cf, and little rij squared. That's the numbers we need to complete this calculation. N is easy. N is the number of observations. In our case, we know N equals 7. Alright. K is easy too. K is the number of measures we taken from each observation. So we have 3 repeated measures. So baseline, month 1, month 2. So K equals 3. Alright. And for CF, CF is the correction factor for tight scores. It's not hard either because it just needs the number, the values of N and K to figure out. So let's figure out the value for the CF. That equals, we know it's 1 over 4 times N times K and times K plus 1. That this value of K plus 1 need to be squared, but I'm just going to do times itself. So times K plus 1. Okay. So what is the value of CF? We have 84 here. Next, in order to figure out the value for RIs, we actually need to rank the scores first. Okay. Again, we're going to rank the scores within the same observation. So I have 1, 2, and 3 for 11, 16, and 17. Right. Next one, I have 1, 2, and 3. I rank the score from the lowest to the highest within the same observation. 1 to the lowest score, and 2 to the next one, 3 to the highest. So far so good, but next one, when we have tight scores, we have 2 2s here. They would take up the rank of 1 and 2. So the average of 1 plus 2 divided by 2 is 1.5. So that would be the 2's take rank 1.5. and the next one is 3. Same thing for the next one. We have 10 and 10 that would have taken the rank of 2 and 3. If you average the two ranks by 2, that would be 2 plus 3 divided by 2. It's 2.5 for each. Okay. Once we complete the ranking, we are ready to calculate the sum of, that's a big R, the sum of ranks within the same measure. So sum of those 7 ranks, and we're going to do this for the 2 months after the baseline month. So month 1 and month 2, we're going to do the same summation. Alright, so now we have R1, R2, R3. Those values will be needed for this part of the formula. Next is this, little rig. This is the square of ranks for each individual score. So I'm going to do this. I know for the first score, the ranks are 2 in the observation, and take a square of itself. It's actually pretty simple. You just need to do the same for everyone in the data set. You just copy and paste. Then every score times self gave you the squared ranks. So for getting this part, it's very simple. The summation of squared ranks, we just simply add all the 21 squared value together. Alright, just to make it simple, I'm going to do this 7, just copy, and that simply add those 7 numbers together. And I'm going to add those 7 numbers together, add those 7 numbers together, and find out the total. Okay, the total here equals this plus this plus this. Okay, so 97 is the sum of squared ranks for this data set. And now I'm ready to calculate the F-statistic. So F equals, for the numerator, let's see, for the numerator, that equals N, which is 7, times K minus 1. K minus 1. And then times, in the parentheses, we're going to put R1 squared. So R1 squared divide by 7 plus R2 squared divide by 7 plus R3 divide by 7. That's this part of the formula. From 1 to 3, we do the R squared divide by 7. Okay, after we complete this part, we subtract CF, which we already know it's 84 right here. Okay, this is the numerator of this F ratio. Okay, divide by, I'm going to just put in a division sign here. Divide by, what's the new denominator? Denominator is, we already figure out the sum of all square ranks, which is 97, minus CF. Okay, so we end up with a F statistic that equals this divide by this. The value is 10.231 for the obtained F statistic. You can decide whether to reject your null hypothesis by comparing your F observed with F critical. The critical value in this case is available in table B.5 at the end of the book. You need to use N, which is 7, K is 3, and alpha equals 0.05 for the critical value. In the table, if you use those three values, you would find a critical value of 7.14. Since the observed 10.231 is greater than 7.14, we are going to reject the null hypothesis. The rejection leads to a conclusion that the manager's strategy by taking money off their paycheck for every time an employee being late is effective in reducing their tardiness. However, you need to know that we know there are some difference between the three medians you have from the three observed from the observed measures. However, at this point, only looking at this F statistic and its critical value, we cannot tell exactly where the differences lie. So we don't know it's a difference between baseline and month 1, or difference between baseline and month 2, or it's between month 1 and month 2. So we need to do additional tests that's called post-hoc tests. Okay, post-hoc tests. In this particular example, the post-hoc test can be used is the one we learned for the two-sample related test. So that's the Wilcoxon signed rank test. Basically, you just compare baseline with month 1. You can compare baseline with month 2. That's what the book did in the example. Or if you're interested, you could also add the comparison between month 1 and month 2. The most important thing to remember when you're conducting the post-hoc test is to make corrections to your alpha value. Okay, if you do multiple tests, your type 1 error will be inflated. So you actually need to take so-called Bufferoni adjustment to your alpha value. It's simple. It's basically just divide your alpha by the number of tests you're going to run. So in the book, the only post-hoc test was done between baseline versus month 1 and baseline versus month 2. So in that case, you use alpha divide by 2 for the two tests. So each test you use alpha equals 0.05 to compare with the p-value provided by the SPSS. Well, if you decided I'm going to run 3 tests, I'm going to do the comparison between baseline and month 1, baseline and month 2, and month 1 and month 2, you actually have to divide your alpha by 3. So divide by the number of tests you're going to run. So each test, when you get the p-value from SPSS, you compare with the 0.0167 you got. That's how you run the post-hoc test for the Friedman test. When you only need to do this when you have a rejection of the null hypothesis. In Friedman test,